So early on, we talked about Ampere discovering something. So one of the things that we saw is that if I have a current in my wire, and I go ahead and apply a current to the wire, so my wire was going in here, that we have this coming and we have this going out, and I have that inside of a magnetic field, that this would cause it to rotate. So this is current in, we get a rotation and torque. And that rotation and torque results in spinning, which means we can do mechanical work. And if you use the water analogy, and I have my water wheel here, I have my water coming down and it causes this to rotate, and I get a rotation here. And this is our mill stream example. That allowed me to do mechanical work. So this was a motor. So my motor required that I have electricity to go in. It's going to cause this magnetic field here is going to produce a rotation, and we're going to get something to happen. Now, we're going to use our same mill stream example. So now I've got my mill stream here, and I've got my water coming in. And if I do this, I can cause this to rotate. And if I put this inside a magnetic field, what we saw yesterday was that changing magnetic field, because this, even though the magnetic field isn't changing, but how my wire sees that magnetic field change. So the wire experiences a changing magnetic field. So my wire is experiencing a changing magnetic field. We know that that results in a current. So this is my mill stream example. We're going to use mechanical work. All of a sudden I can't spell. To do the rotation, and that's going to result in a current. So what we see here, this is using like a hydroelectric. So if we let water through and have water hit a turbine, the turbine is going to spin. The turbine is filled with lots and lots of wires that is causing it to rotate around the magnet, and we get an electric current. My wind turbine does the same thing. The wind blows around the hub. The hub rotates. It's going to rotate around these wires. And so I can do one of two things. I can either rotate the magnet, or I can rotate the wires. And depending on how you fix your generator, depends on which one you're rotating. And if you've ever seen a bicycle generator, you know, like to generate light for on a bicycle, basically what that is, if you've ever seen that, they have something that's on the top This is attached to the tire. This is on the wall of the tire. So this spins. That spins, and inside our little item here is going to generate our electricity. So we get that generation of electricity. Now, if you go to section 20.4 in your text, it talks about how we get our wires. So what'll happen if I have my wire and I just have one loop of wire, you can have what are called slip rings that go around these wires. And that's where we have a little bit of a brush here. It looks like a little bit of a brush. And that picks off the current that we get. Depending on how you put these slip rings on, will tell us whether we get DC current or direct current or AC current, alternating current. And that's basically how you're picking up the electrons off of this wire as the wire is spinning in my magnetic field. Now, if I look at DC current, and what if I'm going to deal with DC current, the way DC current looks as I'm using this generator, it's going to look like this. All right, we get a DC current that looks like that. Now, AC current is going to look like this. And hopefully by now, this looks very familiar. So AC current looks like that, DC current looks like that as it comes off the generator. And what we're doing is this is our maximum current or our maximum potential or our maximum EMF. You know, it doesn't matter how we have that, we get that maximum. And if I'm looking at for alternating current, what this is going to look like is there's my EMF. It's going to be 2 times BL A over 2, because this is my area, right? That's my area. And I'm going to have my frequency or my angular frequency that this is working around, sine omega t. And that gives us our behavior that we see for alternating current in generators. My DC current is going to be a little different, but the reason I'm going to get this kind of behavior is because I'm spinning this in my magnetic field. So that's why you're going to get that piece. And if you look at your pictures in 2014, you can see the difference in these slip rings, which is actually is pretty cool because that's what's happening on your wind turbines. These brushes are there in your turbines that you have in hydroelectric dams. All of these brushes are how we're going to pull that current off and send it to where we want to use it. But if I have AC current, up until now, if we had a circuit, just a regular old circuit, right? I had a battery, and my battery looked at a pump here, and we filled up my charge in my capacitor, and then we had a behavior here in my resistor. And then what we talked about a little bit yesterday is we started to talk about our inductors, and that's our inductor. So this is our battery. This is a voltage. This is going to be a DC circuit. This is a capacitor. This is a resistor. And this is a conductor. Now, this thing is not going to do anything unless I'm opening and closing a switch. All right, that one's not going to do, you know, Once I'm at a steady state, it's just going to hold energy just like my capacitor does. Because remember, this will have a time dependence. That has a time dependence because it's going to take a little bit of time to charge. This has a time dependence because it's resisting change. It doesn't want the current in the circuit to change. So when I have a DC circuit, this is going to have, we're going to see this one charge. Resistors are just going to react as soon as I can get flow through it. And this one is going to resist change. And that's what gives us impedance. Okay, and we got our time dependence associated with that. Now, once I do this with an AC circuit, one of the things that I'm going to change is instead of putting a battery in there, I'm going to use a symbol that looks like this. And then I've got my capacitor, my resistor, and now I have my inductor. Well, if my AC current is always changing, so my current in my system looks like this, guess what happens? This is always going to react. And this is always reacting. Because if I go in hit charge, it's going to start to charge up. And if I switch, it's going to discharge, right? So we have that charging up and we got that discharge. This one is resisting change, but it's also going to charge and discharge. So we get things that look like that. So what we're going to do is we're going to define our voltage. We're going to use a script V for our voltage as our voltage max sine 2 pi times the frequency times time for an AC circuit. Okay, because my voltage is going to vary because I've got this constant change going on. And we've seen this before. Well, if that changes, guess what happens? My current is also going to change. And my current is going to change related to that same frequency. Now, because of that, what's going to happen is I'll get a maximum current, but I'll also have an average current. I'll also have an average voltage. So you'll have that average current or that average voltage. You'll also have an average power. Now, my power at any given time is going to look like power times whatever current that I have squared R. So it just looks just like what we've seen before. Nothing new has changed. Everything's fine. But when we want to deal with this average, because of the behavior of our sine, we're going to use something called the RMS value, the root mean square. And that is going to be our maximum divided by the square root of 2, which is going to work out to be 0.707 times our I max. And so we'll see that average as we go in through, and this is called the root mean square current, and that's what we have. So this relates back to this, and so I can have a change in voltage, that's a root mean square, which is going to be my voltage max, divided by the square root of 2. So if we think about how my system works, okay, if we think about how my system works, so if I have current, this is my current, So this is going to be my I max. And I only have resistors. The voltage max is going to be what we call in phase. So for resistors, we're going to be in phase with the current. Okay? Because my resistors are going to react immediately with whatever's happening in my system. So what we have there is my power average is going to equal my root mean square current times resistor. My voltage root mean square is going to equal my max divided by the square root 2. And I will have my voltage root mean square is going to equal my current root mean square times my resistor. And all these things work hand in hand with my AC current. But remember, we know that I have a time dependence with my capacitor, and I have a time dependence with my inductor. So when I'm doing capacitors, I'm going to do the same kind of thing. All right. And my capacitor, so if we start out with my current, I'm going to draw my current in here. Okay, so there's my current. Now, when I'm at my maximum current, my capacitor, this is the voltage associated with my capacitor, is going to be here. It's going to be maximum when I get to my node. And it's going to be minimum here again. And it's going to come out maximum here again. So this is by time. So this is time. So you can see this. This is time. So we end up saying that for capacitors, it's going to lag. We're going to be out of phase. And we're out of phase by 90 degrees because we're going to be out there 90 degrees. So instead of an R, which does our resistance, in order to explain this, we're going to come up with something that we're going to call capacitive reactance. And it's going to work like a resistor. And our capacitance reactance is going to be a value that looks like this. And it's going to be defined as 1 over 2 pi times my frequency times my capacitor. And then I can plug this into equations just like I do this one. So my voltage root mean square for capacitors is going to look like my current root mean square times my X sub C. Okay, so we've got this one's going to lag, that works out, that we have it work like that. Well, the same thing's going to happen with my inductor, except this time, when I look at it, if I have this, again, this is by time, this is my current, and this is my current max. And let's see if I can draw this right. Okay. I'm down here. Okay. This one is considered to lead, and this is for inductors. It's 90 degrees out of phase. And we're going to come up with an inductance reactance. This is the inductance reactance, and it's going to be defined as 2 pi frequency times L. And again, I can have my change in voltage, RMS is going to be my I RMS, and it's going to be my inductance. So this is out of phase, and it leads because the inductor wants to keep the system the same way. So it's going to be ahead of our change. My capacitors are behind the change. So we're always going to lead when we have those happen, and now we can have that piece. So if I have a circuit that has an R, L, and a C, so it's just like I have all three. So this is called an RLC circuit. And I want to compare and look at my voltage across my circuit. I'm going to get something that we call a impedance. And that's going to be a Z, and it's defined as the square root of R squared plus my XL minus my XC squared. And this we can use to do for an RLC circuit. My voltage RMS is going to equal I max Z. Now, for you all who are headed into medical stuff, this isn't as critical, but we call these phasor diagrams. And if I look at my delta V related to my inductor, my delta V related to my capacitor, and my delta V related to my resistor, this is for resistors. And I'm going to get an addition of my vectors that'll get there. So what I end up with is an arm. This will be my V max. It's going to be my V of my resistor, and this comes from the voltage VL minus VC. And now I can do phases associated with my other items. So this looks at my potential. But I can draw the same diagram where this is Z. This is my XL minus XC, and this is just my resistance. And then this becomes my phasor angle. So phi becomes a phasor angle. Now, for most of you, unless you're going to start working on circuits, and unless you're starting to deal with heavy equipment, particularly rotating equipment, this is just something that you got to be exposed to. All right. But in your house, you have equipment in your house that are on 3 phases. Major air conditioners are on 3 phases. They're going to have inductors in there. They're going to be controlled so that you've got that phase. Your oven, your electric dryer, big pieces of equipment that require a higher power or higher wattage are probably going to be 3-phase. And you know they're 3-phase because they have a different plug, because that plug is very different, right? Not only that, it's on 220 volts instead of 110, because that's what we use. Now that this frequency, if I'm in Europe, is going to be different in Europe because it's going to be 50 hertz. In the US, it's 60 hertz. So we have differences there in terms of grid. But our main grid system is built on 3 phases. We have our 3 phases associated with our inductors, our capacitors, and our resistors. And that becomes important because if you lose a phase, your equipment is not going to behave well. And so pumps, big motors, big compressors, heavy duty electrical equipment, if you lose one of these phases in your systems, life is unpretty. It is a very bad day at the refinery. Yeah, it took me several years before I did not say foul language when the power went out at a refinery. It was not a good day, not a good day. And then I get really good language if we lost a phase. And you guys have probably experienced it, you just don't notice it. If you've ever had been in a grocery store when the power goes out and certain banks of lights will go out, well, that'll also change, it'll change how things that are being done. So that's just a different way of looking at things, and we do these phasor angles. So if you're dealing with an RLC circuit, all right, I'm going to refer you to section in your book, section 21.4. But what you're going to do with RLC circuits, they're going to work like other circuits. You're going to calculate the reactance. And that's going to be your XL and your XC. You're going to use XL and XC with resistance. And that's going to calculate your impedance Z. Then you're going to use your delta V is going to be, if I'm doing the max, it's going to be I max Z. You're going to use your Ohm's law the same way. And then you'll do your delta V R max, which is going to be your I max R. Your delta V for capacitor max is your I max X sub C. And your delta, your potential associated with inductors, is going to be your I max XL. And your phase angle, if you're ever asked to calculate it, it's going to be the tangent phi is related to XL minus XC over R. And this comes from our vector phasor diagrams. Now, for those of you who didn't know it, I am a chemical physicist, so that's my primary area of playing. I've done a lot of light scattering. I've done a lot of research associated with electricity and magnetism. And the only time I've ever done calculations was in circuit class where I had to use this stuff. So it just depends on where you're headed. Now, some of you may be headed to radiology, and this might be some things that you're going to have to account for when you're dealing with your instrumentation. Some of you might be working with other pieces of equipment, and you need to be aware of how that works. MRIs, for example. Those are going to be heavy duty pieces of equipment that are going to be built off a 3-phase. you are using magnetic fields, you're dealing with those things. And so those are going to be areas where you're probably going to see this again. But most of us are going to go, okay, other than the fact that if I lose a phase when the electricity goes out, it's going to damage my refrigerator, or it's going to damage my dryer, or it's going to damage my air conditioner. Most of us don't encounter this unless we're doing electrical engineering. So that's just letting you know that I certainly don't test over a whole lot of this. All right. I don't test over a whole lot of it. So you would just want to be aware of that. Now there's one more thing that we need to talk about, because if you go outside and you come into your house, right? Oh, do you want to talk about power? Right? Just remember that your average power is going to be IRMS, voltage RMS, cosine of whatever phase that we're dealing with. So it calculates the same way. It doesn't make a whole lot of difference. But what I was about to tell you is that the electric lines that come to your house and go into your house, or that we're dealing with pieces of equipment, we have to deal with a transformer. And our transformers can be what we call step up or step down. Because what we're going to do is we're going to change the voltage. Because the higher the voltage, the longer distances we can travel without losing things in an AC circuit. And the lower ones we go in. And so basically what happens is this is kind of an iron block here. And it's going to configure and look an awful lot like our Faraday equipment. Okay. So we have our AC coming in, and we have, this one will have a different number of turns. So this will have N1 turns, this will have N2 turns, and then there's going to be a resistor over here. And this is going to be my input, and this will be my output, or vice versa, depending whether I'm stepping up or stepping down. And my change as we work with transformers is that the current in times my change in voltage in has to equal the current out, change in voltage out. So it's just like what happens is I'm going to change my voltages, so my current is going to change. And my change in voltage 2 is going to equal the number of turns divided by the number of turns, change in voltage 1. So these are what you have outside your house. This is what you probably have inside your electrical box. And you've got a number of other things that are going in here. So we've got a number of pieces that are out there. So what's going to happen is this. And this is where we get. Okay, this all culminates. So we had 4 pieces. We've, over the last 2 weeks, it seems like a lot longer, but over the last 2 weeks, we've covered a lot of stuff. One is we talked about how electric fields work. Okay. And we looked at magnetic fields. Now, both of these dealt with flux. I had my electric flux and I had my magnetic flux. Then we had Faraday's law. And we had Ampere's law. Now, this is all well and good. So we end up with 4 equations, but they didn't quite work. Okay, they didn't quite work. And lucky for you all, you guys don't have to see where the fix is. But it took a person by the name of Maxwell. And this is what makes you feel like, okay, we're all not we all have our special talents. And physicists are mean, cruel, and wicked. Okay, physicists are totally mean, cruel, and wicked. And when you go to graduate school, and you're going into graduate school, and depending on where you're headed, and way back when, what you had to do were take entrance exams. And the physicists always gave you these entrance exams that said, all right, the entrance exam is, there's a problem here. How are you going to fix it? These don't quite work. And Maxwell does it on the entrance exam. It was considered an unsolvable problem. And what he does is he makes a correction that's related to time in Faraday's law. And you go, okay, that just makes us all feel really, really good and really out there. Because one of the things that we found out here is this. If I'm going to plot my electric field, and we have to bring in that time dependence, because remember, when we started doing magnetic fields, we had a time dependence, and it caused the charge to move, and it caused the charge to move with a right-hand direction. All right. But if we look at our electric field, there's my electric field. This is E. All right. And it's going to propagate going down like this. Turns out my magnetic field, because my right-hand rule, right? My magnetic field, my right-hand rule, is going to be perpendicular. And that's my magnetic field. And we already saw that if I did my force due to magnets and my force due to electric, right? We had QVB and we had QE. We already knew that my magnetic field and my electric field were related. So what happened was Maxwell gives us a correction. Hertz starts dealing with antennas, and they show that the speed of light is equal to 1 over the square root of my permittivity of free space for magnetism and my permittivity of free space for electric. Or my speed of light is E divided by B. And we can get what we call electromagnetic waves. And that behavior that we see here, you saw where it came from in dealing with AC current and my magnetism. And so I get those electromagnetic waves. Now, one of the things we're going to find out about light next week is that light has 2 behaviors. It can act like a particle, or it can act like a wave. This explanation allows it to act like a wave. But if you look at how this comes together and I look at how the shapes are, I can think of a packet, and I can think of a wave packet, which gives me my particle behavior. And Newton and a lot of folks fought back and forth about my wave nature of light and my particle nature of light. And we put all these observations together, and the speed of light is equal to 2.99792 times 10 to the 8 meters per second. And for your lab, you're just going to compare it to 3.0 times 10 to the 8 meters per second. Now, the other thing is electromagnetic waves do not need a medium. Mechanical waves needed a medium. So sound waves are a mechanical wave. Light is an electromagnetic wave. And these don't need a medium in order to propagate. Okay? They don't need a medium. So electromagnetic waves travel at the speed of light. And those can be microwaves, ultraviolet, infrared, visible, X-rays, radio waves, gamma rays. All of those are electromagnetic waves, and we get that speed of light. They're going to travel at the speed of light. The electromagnetic waves are transverse waves. They're not a longitudinal wave. They're transverse waves, and we're going to see that when we talk about polarization. They're going to travel as a transverse wave. The ratio of the electric field and the magnetic field equals the speed of light. And they do carry energy and momentum because all waves carry energy. See if I can spell energy and momentum. Okay, and one other thing, because you guys are going to probably be working on your speed of light homework. Okay, remember that the speed of a wave is going to be velocity is distance divided by time. Okay, all right, velocity is distance divided by time. Speed of light is going to equal my frequency times my wavelength. Or if I could do it this would be for a mechanical wave. This is for a mechanical wave. This is for an electromagnetic wave. Remember, frequency is in units of 1/seconds. Wavelength is measured in a distance. So we can actually calculate that. And most of you have had chemistry, so we know the energy of an electromagnetic wave is going to equal Planck's constant, h, times the frequency, or you might see it as this if you're in your chemistry book. And my Planck's constant is 6.63 times 10 to the minus 34 joule seconds. And so each range of my electromagnetic waves have different energies, right? They're going to have different energies. And when we get our electromagnetic spectrum, what you'll see is you'll usually see this with frequency, and you see this in terms of wavelength. And if I do these, visible is kind of in the middle here. And these are short wavelengths. And these are long. These are high energy. And these are lower energy. And these will be like radio waves, microwaves, infrared, and these will be UV, and these will be X-rays, and these will be gamma rays. And electromagnetic waves also have a Doppler effect. Okay, electromagnetic waves also have a Doppler effect. All right, questions?